Okay, so next speaker is Mateo Barros Oruela. He's from Universidad de los Andes in Bogota, Colombia, and he's going to speak about unbounded rank 1 perturbations of self-adjoint operators. So thank you very much. And
good afternoon. In this presentation, I am going to talk about unbounded rank 1 perturbation of self-adjoint operator. Let H a Gilbert space and A self-adjoint operator, and unbounded one perturbation of A is of this form, where psi is a vector, phi is an unbounded linear functional. Or will obtain information on the spectrum of B. We have the following assumptions. Number one, A has simple discrete spectrum. Number two, the spectrum of A is ordered in increasing order. Number three, the spectrum of A is separate. In relation to A and phi, we have the following. Domain of A is a subset of domain of phi. And this composition is a bounded functional. With this, we consider this operator, B. Perfect. We have the characteristic function as follows. Now, let Bn our orthonormal basis of eigenvectors of A and right side in this base. The characteristic function right is in this form. Can we ask, what is the convergence of this series? Recall that the spectrum of A is separate. And for epsilon in this interval, we define our epsilon with the complex plane minus these disks with center in eigenvalues of A and radius epsilon. With this, we have the following theorem. If this series is convergent, then the sum is uniformly convergent in R epsilon. Well, about a spectrum of B. The characteristic function locates the spectrum of B with the following theorem. If we are in the resolvent of A and lambda is a no zero of A, then lambda is in resolvent of B, and resolvent of B is of this form. Now, if lambda is 0 of A, then lambda is in a spectrum of B, and its eigenspace is a span of this vector. Note that the resolvent of B is the sum of two compact operators. Then the following corollary states that B has discrete spectrum. Fine. Now, if we are in the spectrum of A, value lambda sub n is in a spectrum of B if and only if this product is equal to 0. Moreover, if all this is 0, then the geometric multiplicity of lambda sub n is 2. In other ways, the geometric multiplicity is 1. Note that if lambda sub n is in a spectrum of B, this implies that lambda sub n is not a pole of A. Perfect. Now, about algebraic multiplicity. We note that the characteristic function is analytic in resolvent of A, and its derivates is of this form. With this, we have the following theorem. If lambda is in resolvent to A, is a eigenvalue of B, then the algebraic multiplicity of lambda is this. In other case, if lambda is in a spectrum of A, the algebraic multiplicity of lambda is this plus 1. Plus 1. Perfect. Now, I'm going to talk about the distribution of the spectrum of B in the complex plane. For this, we have the following lemma. For epsilon in this interval, then, except for a finite number of eigenvalues of B, all line lie in this disk with center in eigenvalues of A and radius epsilon. The following lemma states that for n layers, there exists a unique eigenvalue of B with algebraic multiplicity 1 that lies in this disk. In graphic, the eigenvalues of B are in red. Note that we have finite eigenvalues in a circle with center in origin. In the other eigenvalues of B lies in this disk with center in eigenvalues of A. Perfect. Let's continue with this result. We have enumeration of the spectrum of B such that each eigenvalue of B appears as many times as its algebraic multiplicity. And more important, the spectrum of B and the spectrum of A is near in L2. Or main result. Now, about array basis. Recall this definition. Let sequence of vectors. This sequence is a array basis if there exists isomorphism such that this sequence is a orthonormal basis. We will see that under certain conditions, B has a array basis of Brooks vectors. Recall that for n layers, this AN space is a span for this vector, and its algebraic multiplicity is 1. We showed that the following. If this sequence is bounded, then this eigenvectors of B is near in L2 to the orthonormal basis of eigenvectors of A. With this, we have the corollary. B has a array basis of Brooks vectors. Now, about inverse problem. Given a subset in the complex plane, can we find conditions should that there exists a perturbation B, such that the spectrum of B is the subset? we find the following conditions. If we can enumerate the subset such that the following condition holds, then there exists a functional phi and psi in H such that the spectrum of B is our subset. Perfect. As an application of this theory, in the article, I want to say this article was motivation of all our theory. They study the following operator with domain, and this operator is first derivative, potential, no local point interaction, where K is L2 function, B is bounded, and rho is a number. If rho is non-zero, this shows that this operator is similar to a simple operator plus a constant, this operator, with this domain, and this operator is first derivative and no local point interaction, where K is an L2, belong to N2. Note that this family of operators have the same domain. Study the spectrum of these operators is the same that study the spectrum of this operator. Perfect. Now, let's see the functional evaluation in 2π. Then, this operator can be expressed of this form. Note that this operator is a rank one unbounded perturbation of this operator. Now, for A, consider this operator and phi functional evaluation in 2π, we have the following. In relation to A is a self-adjoint operator. Number 2, the spectrum of A is the integer set, and these eigenvalues have the geometric multiplicity 1. Number 3, the eigenfunctions of A are of this form. In relation to A and phi, we have the following. Domain to A is a subset of domain of phi. This composition is a unbounded functional. Note that we have all the assumptions of our theory. With this, we consider B as this operator. Now, we can the characteristic function of B, that is this operator. The characteristic function is of this form, equaling to 0 to locate the eigenvalues of B. We have obtained this equation. This equation was obtained in the article. Perfect. Now, about array basis. Recall our result. In this case, the eigenfunctions of A are of this form. evaluating the functional phi in this function, we see that this sequence is bounded. Therefore, this operator has a Riemann basis of Brooks vector. Finally, we have the following result about inverse problem. If we have a sequence such that this sequence is near in L2 to the integer set, then there exists K in L2 such that the spectrum of this operator is our sequence. Fine. Thank you.
Thank you so much.